Hello everyone. Today we will be exploring how the finite difference eigenmode solver can be used to analyze waveguide structures and understand their electromagnetic behavior through simulation. The finite difference algorithm is used to mesh waveguide geometries, enabling accurate modeling of complex structures. Maxwell's equations are then solved as an eigenvalue problem to compute key parameters such as effective index and mode profiles. The FDE solver analyzes waveguides using a cross-sectional mesh, capturing mode profiles, losses, and frequency-dependent effects like dispersion and group delay, while efficiently representing complex electromagnetic behavior. Let us now look at the model. Here, a waveguide structure has been defined. The red region represents the waveguide core, while the surrounding regions represent the cladding. The structure also includes the substrate, followed by the lower and upper cladding layers, and finally the waveguide core itself. The distinction between these regions is based on their refractive indices. The waveguide core is made of silicon, which has a higher refractive index of approximately 3. In contrast, the surrounding cladding is composed of silicon dioxide, shown in gray, which has a lower refractive index. This difference in refractive index enables light confinement within the core. Moving on to meshing, the mesh has been primarily applied to the central region, focusing on the waveguide core. The FDE solver utilizes a rectangular Cartesian mesh. In general, a finer mesh results in higher simulation accuracy. In this case, the mesh is refined around the core structure to ensure precise results. By selecting the waveguide region for meshing, the solver prioritizes accuracy where it matters most. Next, the FDE solver region is defined to include both core and cladding areas. The simulation runs at 300K as a 2DZ normal setup in the XY plane. The simulation domain is defined by the X and Y spans. In this setup, the X span ranges from -1.5 to 1.5. The mesh cell size is initially set to 50 by 50, but this can be increased to 100 or 200 for improved accuracy, depending on computational requirements. Boundary conditions are another important aspect of the setup. In this case, the boundary condition is set to metal, although other options such as PML, symmetric and anti-symmetric boundaries are also available. For meshing variants, options like conformal variants and staircase meshing are provided, and here conformal variant 1 has been selected. The wavelength range for the simulation is defined from 1.5 to 1.6 micrometers. Other parameters such as impedance and constants are kept at their default values. Once the setup is complete, the simulation can be executed. After running the simulation, the eigenmode analysis window provides insights into the results. By observing the mesh structure, the waveguide geometry becomes visible along with its refractive index distribution. The color scale indicates the refractive index values, where the waveguide core appears in red with a refractive index above 3.3, while the cladding appears in blue with a refractive index around 1.5. The next step is mode calculation. In this setup, the number of trial modes is set to 20, resulting in 20 computed modes. Among these, the first mode represents the fundamental mode. The remaining modes are typically lossy, as they do not propagate effectively within the core. This occurs because the waveguide dimensions are designed to support only the fundamental mode. As a result, higher order modes are not confined within the core and are therefore considered lossy. This workflow demonstrates a straightforward and effective approach to designing and simulating a waveguide using the finite difference eigenmode solver. Thank you. If you are interested in the full webinar, please visit our website